So this is week 1. We will talk about electrical safety, and this is pertaining chapter 1 in the book. So chapter 1 is all about electrical safety. So I really hope that you skim through the chapter. It's not that long, and it's very, very important. I'll spend a lot of time talking about safety, and I'll always remind you of safety, things that you have to do with electricity. A lot of people disregard or do not pay attention to electrical safety because with electricity, unlike water, you don't see it. It's there, it's all around us, a lot of voltage. So just because you don't see it, you don't feel it, it doesn't mean it's not there. It is there, and we have to be aware of that. So I'm going to tell you some stuff. It might be a little scary, but it's good to be afraid and have the proper respect for electricity. Probably Sean can agree with you. We will work with high voltage. We will work from 24 volts up to 10,000 volts. So 10,000 volt can be fatal. And you probably always hear people telling you, oh, it's the voltage that kills you, not the amperage. It's the amperage, not the voltage. It's both. It's both. Amperage can be fatal, and voltage can be fatal as well. So electrical current and the human body. So, do we have electricity in our body?
Yes.
Yes. Without electricity, you will not be able to think. You will faint. The brain sends microvolts to your muscles to contract. As I'm moving right now, my brain is sending a lot of signals to my body. Your heart has a preset system that keep it pulsating back and forth, and that's why some people, when they get heart problems, they require a pacemaker, which is a small little battery that they put into your body that will send signals to the muscles to contract. If you've seen, I don't know, back in the 80s, they used to have those machines that you play into your muscles, and they will exercise your muscle while you're sitting down, just by sending voltage to it. They don't do that anymore, right?
I think they still have one for your abs.
Yeah?
I think so.
You'll be sitting in the office until just like 10 small voltage, so your muscle will contract and retract. So your muscles require contraction and voltage to be able to contract. If you do any of those mad scientist videos on frog legs or dissecting animals, and you can run small voltage into the muscle, dead muscle, and it will move, it will contract. So there's a lot of electrical signals in our body. Your body is full of electrolytes. Probably you guys work out, you always think about electrolytes. What are those? Electrolytes are small little ions or salts in the water fluid that enable your body to conduct electricity. If you have no ions, it's not going to be conductive. I will talk about conductivity as well and what makes things conductive and not conductive. When you use a lot of electrolytes, a lot of salts, the pure water is not conductive, right? You agree? If you have pure distilled water, it's not conductive. Once you add a few grains of salt, it's become conductive. So your body has to remain conductive. If it's not conductive, it's not going to transmit signals. You might have paralysis. And that's why in the sun, when you sweat too much, you start like fainting, because signals are getting disrupted in your body. So you're not going to be able to control your body. So you need some salts. People who work in the heat, they sweat off, they need to eat some salt to replenish the electrolyte. If you don't have that, again, you get fatigue, eventually you'll pass out, and your body's not going to function. Types of injuries that can happen from electrical current. Burns, what else?
All of these is in the book, right?
Yeah, everything here is in the book. Okay. So, types of injuries that you can get from electrical currents. You can get burns, you can get paralysis. If you run enough voltage through your heart, you might mess up the wiring there. Again, we said it's very, very small, very millivolt. So imagine how thin those nerve systems are. And if you run a lot of voltage, you will burn it. You destroy the path. So it might be an issue. So if you get zapped with enough voltage, went through your heart from arm to arm, you're probably going to need to go see a doctor because your heart might not function properly. Hopefully you'll survive it. But this is what happens. And we talked also about the muscles contraction. So what happens? So we'll talk about that as well. And why does somebody, when they touch an electrical wire or something that's live, they cannot let go. Why can't they let go?
Okay.
Muscles are contracting because they're running through electricity. So somebody who actually touches a wire, the muscle will involuntarily contract and grab into things. So what would we do if somebody is electrocuted and they cannot let go? The muscles are paralyzed.
Kick away.
You have to push away with something non-conductive. You don't want to break his bones, do you know? You gotta push him with a non-conductive material, and we'll talk about what is conductive and what is non-conductive, and what is grounding, and why do we have grounding, and what is the purpose of that. We'll talk about some also safety procedures. So we'll tackle these items one by one, and I hope you really understand it and embody it, especially when you go in the lab with Brad and try to work with some stuff. Don't just learn it here and forget it when you do actual wiring. So when you wire a board, it is live. It is 110. It will zap you. So be aware of that. Think about the ground. Where is the ground? Think of the GFCI that we have. We'll talk about all these things one by one. So electricity in the human body, the nervous system is completely electrical. It's completely electrical. Your brain is an organ that's made out of fat cells, and has a lot of electrolytes in it, and it does thinking, God knows how, but there's a lot of small little currents running through your brain. And that's why they think at some point they can put a USB in your brain and download stuff. Somebody's working on that. Some mad science. They are working on that. They can download things into your brain. That'll be amazing, you know. Download the whole program. The interface between biology and machine is getting sooner. And Skynet will happen. The rise of the machine. But the nervous system is completely electrical. This is how you control your body. This is how you move. It's synchronized muscles, and that's why also when some people lose limbs, now this is actual science. When somebody loses a limb, they can put a mechanical arm or leg, and you can control it using your nervous system, the nerve ends. So this is actually happening now. So your nervous system is completely electrical. Plasma TV. What is plasma TV? Plasma TV is the same thing. Plasma is a word for something that's ionized. It's something to become ionized. What does that mean? That means the electrons there are full of energy. So plasma is ionized gas. And if anybody took physics, we used to have three forms of material, right? Solid, liquid, and gas. And now they have plasma. When I was in high school, there was no plasma. Now they have plasma. Plasma is, after you have gas, if you heat it enough, it will become ionized gas and it will become plasma. This is the base of plasma TV. Your body has plasma. Your blood has white cells and red cells, and also plasma. Plasma is where you keep your salts, and we keep conducting electricity. And that's where the electrolytes are. Electrolytes are salts decomposed. Salt is, what about table salt? That's sodium chloride. When you dissolve that sodium chloride into the water, it can decompose into sodium and chloride and become ionized. It can carry electrons and signals. So when you sweat, the sweat has salt in it, right? So the sweat has salt, so you're losing salt. If you sweat some more and you just drink water, you're not replenishing the salt, and that's what leads you to lose electrolytes, and eventually you'll faint and lose control over your body. That's why when you eat a lot of salty food, you feel bloated, because salt loves water. So your body will have a lot of salt or water retention. You have to drink a lot of water, get rid of water, which seems kind of like oxymoron. But you drink a lot of water, so the salt will get attached to the water, and then you urinate. So you keep drinking water to get rid of salt. So salt and water is a very interesting relationship. So sweat has a lot of salt. Salt content in the body is important, so you cannot have a salt-free diet, but you want some salt in your diet. And salt was very praised food for a long time because it's really hard to get, and they think the food tasty because we want salt. Your body needs the salt. Animals travel long distances just to get some salt, whether sea salt or like salt deposits. So it's very, very important. So we need salt. Conduction. What do I mean when I say conduction? When something conduct, it transfer something from one place to another. That is conduction. Conduction happens in minerals and metals because they have loose electrons. Every material can conduct at the right voltage. Remember that. There is no absolute insulator. Do you think air is a good insulator? Air is a good insulator, but you think it will conduct? Yes, air will conduct. At 10,000 volts, you'll see that the spark jumps from one channel to another. The higher voltage you get, it will go from one place to another. That's why we have thunder from the clouds, conductivity. So air does conduct. Does rubber conduct? Yes. At the right voltage, it will conduct. The more voltage you have, the more insulation you need. I'll show you an underground wire for electricity. That's 4,000 volts. So look at this insulation, and probably this is around 4,000 volt going through it, and this is the amount of insulation you need. This is underground wire, and if you increase the amount of voltage, it will conduct. So you never touch a wire, even though it's insulated, because you never know how much voltage going through it. So this gauge is maybe 000. Yeah, 0040. Look at the bundle of the cables and how much insulation it requires. Heart function and the brain function, they are both dependent on electricity in the body. If you mess that up, you might pass out and you might be crippled. There are stories where people go do a job, a lot of wires, they don't pay attention. They work on a job, they're sweaty, your arm touches a pipe, and you get zapped. So be very careful. You're working with boilers and ACs. There's a lot of wetness, a lot of wires, and not every house is very neat and orderly. You're gonna have loose wire here, loose wire there, and your best friend will be your voltmeter. You have to go there and check this voltage. Make sure there's no voltage. Check, triple check everything, and we'll go through the safety procedures. Again, there's always a story in the HVAC magazine of somebody going to a crawl space in the dark by himself, and he gets zapped. It doesn't take much. How long does it take for the brain to start dying? Within 3 minutes. So if you have no oxygen, your lung function stopped, your brain start dying after 3 minutes. So 3 minutes of no oxygen, that will be fatal. So with safety procedure is cut off the power, tell somebody going to be there, and post a note. I will talk about this procedure. Heat and ignition. So we'll talk about heat and ignition. And this is how we ignite a lot of our fuel. So spark has heat, and that heat can be very, very high at the middle of the spark, and that will ignite gases at the right molecular size. That's what you have in your car, right? Don't you have spark plugs? How much the voltage in the spark plugs? Usually around 10, 15,000. If you have a sports car, probably you have more than that, 30,000 volts. So that's a lot of voltage, and that small little spark has a lot of heat, and that's what ignites the gas. Your cigarette lighter has butane gas, and there's a spark, and that spark is really hot. So spark has heat. That's how you do welding, right? Arc welding, you're running 40,000, 30,000, and the metal melts. So if you're melting metal, you know the temperature there is above 1,000 degrees. So that's a lot of temperature, and you should give it proper respect. So it can't melt stuff. I melted a screwdriver once in a car by mistake, touching two terminals together. It just fell in the battery and it just melted. That's how big the spark is. So I know somebody was wearing a metal watch. He was working with wires, and they just touched the whole band melted. Put this hand too, of course, a little bit. So be very careful. Don't wear anything that will attract electricity. Again, conductors, metals, sometimes ceramics do conduct, to a limit. But heat and ignition and electric shock. So shocks can, let's say you get high voltage with a lot of current. It will still can burn. It can throw you off a ladder, and it can also zap your system, and you don't know what happened to your nervous system. Who has been zapped before? What does it feel like? 110? 220? What was the voltage?
Yeah, electrical fence.
Yeah. Oh. That is something. So I tried that. No, not on purpose, but I did get zapped by 110, 220. After it takes a while for your arm to start not feeling numb. Stop feeling numb. You get numbness for a while, and you should get checked. So it's a big deal. So be careful. I'm not trying to scare you. Just be careful. Take precautions. Don't trust any wire that's not live. Don't get excited touching wire that look dead. So make sure to look at the plug. And some equipment, even though they're unplugged, they can still have charge. Why? Capacitors are dangerous. And I'll show you what is the proper way to discharge the capacitor. It can carry up to 4,800 volts. That's a big spark. If you have gas in the vicinity, you'll lit up the gas. So spark has a lot of ignition and a lot of power. Even a small spark. You see in the action movies, usually when the villain comes in and he wants to burn down an apartment, you let the gas out and set the thermostat and leave. Because back in the day, they used to have a spark in the thermostat, small spark. I don't know if this actually happens, but it seems kind of cool. So, huh? Yeah. Which one, Eraser?
Yep.
I don't think it even happens, but there's a small spark in this thermostat. In theory, it could happen, but I think it was debunked. But it's possible. Small spark can do that if you have enough gas, enough density of gas. And eventually, most of the thermostat now are not springs, and there's not a lot of spark in it. What's a live circuit? A circuit that has electricity going through it. That's live. There's voltage. And you will never know until you go and use a voltmeter. So I want you to invest. I'm going to go bring a voltmeter just to show you. So voltmeters comes in many shapes and colors. They range in price from $5 to $30. This is supposedly one of the most sensitive ones. The Fluke, this is I think $30. You can get it for $25 on Amazon. That's a good investment to have in your pocket. So if you can put that in your Christmas list or get it somehow, it's very useful. Usually I buy a lot of those, but by the end of the semester they disappear. So if you can, please buy one. I'm sure Brad will be very happy. But you can use that against any wire and to light up if there's electricity. This is dead. What about here? So see, it's lighting up. And there's voltage going through it. But it's going to be at least the first line of protection to know if there's power or not. It lights up blue if something not hot. We'll talk about hot and neutral. But blue is like there's current going through it, but not a lot. Red is there's actual voltage, 120 volts. There are other ones that are cheaper, but they're not as sensitive. So you have to be really close to see voltage. I find this one is more useful to see where the voltage is. So you want to know where the voltage is coming from. So live circuit is any circuit that has electricity going through it. Unplugged system. Is it always safe? We said no. It could be a capacitor. It could be a battery. A capacitor can be really big, and they hold charge for 48 hours sometimes longer. So how do you discharge a capacitor? There are two ways. There's the scary way and non-scary way. The scary way, you touch them with a big screwdriver that is insulated. But I'm always very like, but it's gonna be a big spark. So it's always very scary. The non-scary way is you buy 1 kilo ohm resistor, keep it in your wallet, you just touch the terminals for 2 seconds, and it will discharge the whole thing. I'll give you one for free. Keep it in your wallet. At least for that purpose. I don't know who goes around with it. I have a resistor in my pocket just for this purpose only. Current and voltage effect, which is more harmful. They're all harmful depending on how much current and how much voltage. So high voltage is going to be harmful for you, and also the current. So a car battery, even though it's 12 volts, has a lot of current. So don't stick your finger in the cigarette lighter. It's a lot of current. This thing can operate the car equipment. It has a lot of current in it, but it's low voltage. Again, a transformer igniter doesn't have a lot of current, but it's 10,000 volts. That thing will burn. So shock or burn by high voltage, that's something you don't want. Heart function, beat and flutter. So your beat has been set since you were born to be at a certain rhythm, and so is your lung function. The diaphragm going up and down is where you sit. If you miss that function by running a lot of voltage through it, you're gonna have to, at some point, put a pacemaker. Sometimes it comes back, sometimes it doesn't. What do you think happened when they try to defibrillate somebody? When somebody having a heart attack? What do you think is happening? That's actually 40,000 volts.
Trying to get that rhythm back.
No, it's actually reset the whole thing. Get rid of all the signals, and hopefully it will start. And actually, by the way, it's doing a lot of damage to your system, but at least you're alive. But the damage it does is huge to your body. So don't do it if you don't need to. So what happens is like so much voltage that wipes out all the entire current from your system, and hopefully it will start again. Sometimes it does, sometimes it doesn't. As you see, the body just jumps, right? At least in the movies. I haven't seen it. I haven't seen it in real life. But it's a lot of voltage. So 40,000 volts, you shock somebody, hopefully it will come back, and sometimes it doesn't. Sometimes it comes with missing a beat. If you get zapped, please go see a doctor. Let me know. And because sometimes you don't notice something, you have to put you in an EKG machine and make sure the heartbeat is going regular. So you're not skipping a beat or anything. And again, what happens is you get zapped, nobody knows you're there, you lose breathing, and you start like brain stuff down. Sorry if this seems a little scary, but I want you to have the proper respect for electricity. Don't disregard it. So current. We haven't talked about the difference between what is current and what is voltage. So current is the flow of electricity. Voltage is the electrical potential. So voltage is electrical potential. We're going to do some nice analogy here. They always compare electricity to water. The water flow, the water circuit in your house. So voltage, if you have a water flow, will be, this is the pressure, water pressure. Current, water flow. Resistance will be the pipe size. Or tap. Let's think about that a little bit. If you have a tank of water that is in the third floor, it has a lot of potential, right? A lot of pressure to go down. The water comes to your house from the municipality with a lot of pressure. That is your voltage. It's the same thing. Water has to run through the pipes. That's your wires. And your water flow is controlled by the pressure and how big the pipe is. So if the pipe, if the resistance, electricity is the pipe, so a big pipe will have more flow and less pressure. And your current will go through a small pipe really fast with high pressure. Think of the garden hose again. This is your pressure in your hand. If you squeeze in on it, the pressure is going to be constant. Your flow is going to be faster and the velocity will be faster. And you're putting more resistance in it. So resistance, pushing on it, they'll give you more flow. I mean, more pressure, less flow. So some terminology, we'll talk about it more until I'm blue in the face. It's, but I want you to know voltage is electrical difference, high voltage and low voltage, and always things want to go to balance. Like high pressure would love to go to low pressure. Water in the mountains want to come down to the sea. It's the natural order of things. Things always want to be in balance. So we are producing voltage so we can let the electricity flow. And current is the flow of electrons in the wires. Just how we make the water flow into the pipe. And the resistance is what we're using to do work. So it's just how we can use the water to turn a turbine. We can use electricity to turn a motor. The same analogy. Water goes in current, and electricity goes in current. We'll talk about that in a lot of details. So current is the flow of electricity. So at 0.00 amp, that's very small. A small toothpick, water pick. So you feel something. 0.02 amps, you might get stuck. This might activate your muscles, and you're gonna get stuck. It's not going to move. And again, your body has a lot of electrolytes. It's going to be attracted to the electricity. You will get stuck. 0.1, ventricular fibrillation. Your heart will start like getting confused. Muscles gonna be fluttering everywhere. Somebody will be shaking. They're confused. They don't know. Should we contract or relax? So, 0.2, severe brain and respiratory paralysis. So, for 0.15, between those two, the truth lies. That's when it's going to be fatal. So 0.015, that will be fatal. And it's in the book. If you look it up, I'm going to go by the book. They say 0.15, 0.015 is what gets you stuck. And I think you'll find that in page. It still seems a little bit low, but it's enough to get you stuck. It's somewhere in here. Take my word for it. 0.015. I'll write it down. So this is for current.
Page 6.
Page 6, you got it? Is it the same?
So the current flow through the body of 0.015 ampere or
Yeah.
less can prove fatal.
And depends, so it can be, depending on where does it flow. I will talk about that in pictures. If it flows across your arms, no good. No bueno. Your heart is in the way. If you touch your arm and foot, you might get away with it. But across your chest, it's very, very fatal. Moving on. It's here or less can flood your body. So a light bulb, 60 watts of light bulb draws 0.5 amps. So if you touch a light bulb the wrong way, exposed, you might get stuck and you might be fatal, and just the light bulb. Electrical shock, which being zapped, and can be thrown off the ladder. The muscle completely contract. So we always use an unconductive ladder. And that will lead us to what's an unconductive material. So non-conductive material, it's something that's not metal, not salt, and not semiconductor. What are semiconductors? Silicons, ceramics, glass, those are kind of fall in the same category. So non-conductive material, wood. What is wood made of?
Trees.
What is tree made of? What is every living organism made of?
Matter.
Carbon. Carbon atom is the basis of life. So all organic material are based with carbon. So carbon is not a very good conductive material because it has 4 electrons in the last orbits. You don't have to worry about that. Don't think about that. But it's not conductive because it's very stable. And we'll talk about the atoms and what is it. Some fabrics are not conductive, not all of them, depending what they're made of. Cotton is organic is not conductive. Plastics, what are plastics and rubbers? Hydrocarbon, organic material, non-conductive. So think of carbon, non-conductive. And again, everything is conductive at the right voltage. So just because you are wearing rubber gloves, you're not impervious to electricity. There are some special gloves for each amount of voltage. So don't trust voltage.
Get them tested regularly too.
Huh?
Get them tested regularly
Yeah.
too.
Do you know why birds are not gives up? Because they're not conducting, right?
What's that?
When birds stand on the power line,
Yeah, yeah, they don't get that.
yeah, because they're not touching something else, right?
Yeah.
So if they touch something else, they will get zapped, right? I always wonder about that. But the idea, I'm not sure about that. Don't quote me on that. The idea that they're standing on the power line and they're not touching anything else.
Yeah.
So
The
Huh?
legs.
yeah, maybe if they hold something and moving the power line. What movie was it when they put their jacket around the power line and just drag down and they jump? I used to love actually when I was young. So they put a belt around the power line and zap down before they touch the ground, they jump. So they're not conducting. So again, the idea is conducting electricity through you. Is it conducting through you? And that's why you wear rubber insole boots. Because if the power is not going through you, you're not going to get hurt. But I think it's the same idea. So thick rubber insole is really good because again, power is not going to go through your body. And again, the high pressure always goes to which path? The path of least resistance. And the earth is the biggest conductor. So if you're touching something and going to the earth, everything want to go to the ground. And that's why we have ground, and we'll talk about that. Always the path of least resistance. The ground is a big, huge conductor, and everything wants to go back to the ground. That's the code. I'll put the link for the NEC, National Electric Code. The code changes every year. Always check the code. This is the national code, the federal code. The state code can be either higher or equal. The county code can be higher than the state, higher than the federal, or equal. So this is the national code, which is the bare minimum code that you have to use for wiring and conductors. Grounding. So the ground, again, we said the path of least resistance. You want the electricity to go to the path of least resistance, which means the ground is the biggest conductor. What does the ground have? Rocks, sand. What is sand? Sand basically is silicon. Silicon is a semiconductor, among other materials. It has salt, it has water, it's going to conduct. So what does ground do? It lets the current flow back through the ground instead of through the person. Because if you have a ground, the electricity or the current will choose the path of least resistance. The ground is bigger path than you, so I'm just going to go to the ground. And that's why we have ground. And for example here, is our ground. If this person touches, he's doing a power tool. If he touches if there's a loose wire here that's touching the case, went through the guy's body, and not the ground. And he's touching something that's grounded, even though he's wearing shoes. This ground here, this object, whatever it is touching the ground, so the current will go through him to that object. You have provided a path for the electricity to go through you to the ground. If you have a ground in the wire, in the plug itself, if there is anything in here that is loose, it's gonna rather go to the ground than to go to you. You get the concept? That you don't want to be part of the circuit, you're gonna give the circuit another option. A huge path to follow so it does not go through you. And that's why we have the ground that people always break. You do not break the ground. And it's by code now, every house has to have a ground. So the ground is always, probably this handrail has a casing. The case is made out of metal. And if anything in the motor inside the drill gets loose, it will touch the casing. And the casing is connected to the ground, and the ground will go into the actual ground in the ground. And it's called ground because it is in the ground. Back in the days, they used to use the ground as the pipe, the water pipes. But that changed because the water pipe is in the ground, it's metallic, so they used to just put the ground in the pipes. So eventually it will go into the pipe. But what if somebody's in the shower? So now they have an actual ground. It's a big piece of metal made out of copper, and they bury it, and they connect the whole entire house to it. If you look at the electrical socket, it's made out of metal on purpose. All the conduit made out of metal on purpose because they want that to be the ground. If something breaks loose, it's going to touch the casing, and the casing is connected to the ground. So when somebody does touch something, if you go touch the switch and something is loose, you're not going to be affected. And the circuit breaker should trip because it tells you the ground has been activated. In the bathroom, you see that little receptacle with the light in it? It's all in the bathroom. That is what's called GFCI, ground circuit interrupter. What happens is you're washing your hands, you're becoming a conductor like this person here. You are conductive because you have water in your hand, and something is loose and touching the casing, it will go directly to the ground and trip the circuit right away. So probably see that in the bathroom a lot. Usually, actually, it is the code to have it in the bathroom. Wherever there's water, it has to be a ground. Most of our receptacles here are GFCI, just in case the ground is activated. So if the ground is activated, it will shut off the circuit right away. And that's good to have a ground. I'll have a picture of the ground. Another case where you can touch the ground and you become the path instead of the actual ground. So you're working with a wire, there's a loose wire here, you become part of the circuit and the current goes through you to the ground because that's the easier path instead of going over here. So be aware of that, be aware of what are you touching when you're working with live circuit. It's live. This is a picture about the actual ground. The color for the ground is always green or bare wire, bare copper. So either copper wire or green. That is the good ground. And again, it is the code to have the ground. Never disconnect the ground. All appliances that have high amperage, they have ground. Microwave, oven, space heaters, they also have ground. What do you do if you have an equipment with a ground and the socket doesn't have a ground? What are you going to do? Do not, under any circumstances, break the ground. What do? You can buy a small adapter. There's a plug that converts a 3-prong into 2 prongs and has a fuse in it. The fuse will burn if the ground is activated. So that's what you do. Yeah.
So almost a little ones you buy that are like 3 in a pack.
Yeah.
No, they're great.
It has to be 3 prongs and go into 2.
Yeah.
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 And they have a fuse in them.
What I do?
Yeah. And don't buy one without a fuse. Don't buy the Ocean Job Lot or the Harbor Freight one without fuse.
That's all
Buy
I'm
one-
asking.
Yeah. No, buy the one with the fuse in it because there's a reason for that.
Okay.
So the fuse is to protect you in case something happens to the equipment. And again, power tools draw a lot of power. So anything that draws a lot of power, have a fuse in it. One thing you do not want to skip on is power strips. A good power strip is expensive, and you should pay the money. Don't pay the $2 power strip or extension cord. Make sure it's the right size wire. And most of household fires are electrical. You overloaded the circuit, you have really cheap extension cord. Yeah, there's one for $15, one for $2. Get the $15 one. Otherwise, you're going to pay a lot of money for fire. And you can see the wire are thick per coat, has a ground, and also it has what's it called? Surge protector. It used to be very common back in the days to have a surge, especially if there's a storm or something. You might have surging power, and this will trip instead of burning your equipment. Like when we used to buy computers back in the days, you have to buy a power stabilizer. And also, if you buy a laptop, usually the original transformer has a protection in it. If you buy the aftermarket one, probably going to ruin your computer and your battery. So these are kind of little things that you don't want to skip on. Anything that has to do with electricity, buy the good quality ones. Because again, they are designed to protect you from power surges and faults. This is ground equipment. Most of our equipment has to be grounded, and all receptacles has to be in the ground. This is the ground rod. Again, big copper rod in the ground, and you have to plug into it. Why copper? Huh? It's good. It's a good conductor. What is the best conductor?
Gold,
Gold. Second,
silver,
silver. Third is copper. Nobody wants to use silver and gold. It's very expensive. So copper is the best alternative. What's after copper? Aluminum. So if you see some equipment from the 1950s or 60s, probably you see a lot of copper wiring. I mean, aluminum wiring. And the reason being is during World War II, there was a shortage of copper. Copper is still expensive. Recycled copper is $2 a pound, sometimes more than that. So it's very expensive. It's completely recyclable, and it's a very, very good conductor. Your cell phone or your computer, the CPU has gold connectors in it, and the circuit is printed in gold. That's why it's expensive. The processor in your computer is the most expensive part. It's not less than $1,000, $700, $800. Your phone chip has some gold in it because gold again is the best conductor. But in that size, it's not that expensive. Not that a lot. So gold, silver, copper, then aluminum. So we want something that's really going to be attractive to electricity, to ground ourselves, and to ground any excess electricity in there. So again, this is the actual receptacle, power receptacle, and it has a ground that has to be connected. This connect to the casing. And this is our prong with the wire. This is what I was talking about, the surge protectors. There are some special adapters you can put to convert 3 prongs into 2 prongs. Do not cut or remove third prong. Only equipment with only an equipment with possible short. If there's a possible short or a lot of current going through it, probably you're gonna put some prongs. I'm gonna pause the video and start again. It's getting long.